Welcome everyone. So today's lecture will focus on designing a full adder using half adders. So by using a hierarchical design approach in Tanner Edit. So as we know that the half adder and the full adders are the two important components which are used in digital electronics, right? So these circuits are used to perform binary addition. This binary addition is fundamental in processors and other digital systems. So we will begin by creating a half adder circuit first. So then use this submodule to design a full adder. So the hierarchical method will allow us to reuse the smaller or verified components such as half adders to build the more complex systems like full adders. So a half adder is a basic digital circuit that adds two binary digits, right? So this is the circuit and this is the truth table of a simple half adder circuit. So a half adder circuit, it will consist of two input variables A and B. So these two input variables accepts the inputs like binary digits, either 0 or 1. Likewise, so it consists of two output variables, sum and carry. Okay. So now we will see how this half adder will work. So here the sum output gives the result of the addition of two input variables A and B. Whereas coming to carry output, so it is set to 1 only if both inputs are 1. So if both inputs are 1, then only the carry output will be 1. It will indicate an overflow of the carry bit. Okay. So the carry output is set to 1 if both the inputs are 1. So it will indicate an overflow. So when A and B are both 1, the sum is 0 and the carry is 1. So this happens because, so 1 plus 1 in binary equals 1, 0. So which is 2 in decimal, right? So if you observe the circuit, so the circuit uses one XOR gate and one AND gate for the carry. So why we are specially using XOR and AND? So once if you observe the truth table of this half adder and if you observe the combination of outputs which are present under the sum, so the combination is like 0, 1, 1, 0. So if you observe it clearly, so this output combination, so we will get for the XOR gate, right? So that's why. So to get the value of sum, we need to use one XOR gate. And similarly, if you observe the output combination of this carry, so the values are like 0, 0, 0, 1. So this output combination we will get for the AND gate, right? So that's why to get the value of carry, we need to use one AND gate here. So clear. So this is all about the half adder circuit. So now we will move to the full adder circuit. So this is the total circuit diagram of a full adder circuit. So if you observe this circuit closely, so this circuit consists of three input variables A, B and C in. So the full adder can handle the carry input from the previous addition. So which makes it suitable for adding multi-bit binary numbers. So it uses two XOR gates to get the final sum and it uses two AND gates along with one OR gate to get the final carry out. So if you observe the circuit closely, so the combination of this XOR and AND gates will result in a half adder circuit, right? So by combining two half adder circuit along with one OR gate, so we will get the full adder circuit. So now in this session, so today first we build a half adder circuit. So first we build an half adder circuit by using an XOR and AND gate. So after using that half adder circuit, so we will design the full adder circuit by using the hierarchical design approach in the Tanner Edit. Okay. Now we will design this half adder and full adder in Tanner Edit. So for that, so just to open the Tanner Edit. So to launch the Tanner Edit, so just to go to the search bar and search for Edit. So after getting the app, so just give a double click to launch the Edit. So once the Tanner EDA is open, so follow along as we create this schematic. So for both half adder and full adder circuits. So after opening the Tanner SEdit, now we need to create a new design. So for that, go to File and select New. Here, select the new design. So here I am giving this design name as half adder underscore full adder. So this is my design name. So here you need to choose your directory. So to save your design. So after choosing the directory, so just click on OK over here. So now my new design is created. So you can see it over here. So after creating a new design, so after creating a new design file, so now we need to add the standard libraries to our design or to our project, right? So how to add the standard libraries? So that we have already discussed in the previous session, right? So to add the standard libraries to our design, so we need to just click on this add option over here. And now we need to browse our standard libraries. So for that, just click on the browse option. So in the process folder, so we will find a generic 250nm folder over here. So to design the full adder and half adder circuits, here we need some basic logic gates like XOR and NOR gates, right? So those gates will be present in this generic 250nm logic gates folder. So if you open this here, you will find the Tanner design for our basic logic gates. So just select that file and click on open. So, and again click on OK here. So now a generic 250nm logic gate standard library is added to our design. So next, we need to add some spice commands. So for that, so just follow the same process. Go to process folder. Here go to this standard libraries folder. So here just select spice command file. So click on open and click on OK. So now we need to add one more file. So that is spice measure. So select this one and open and finally click on OK. So now, so we added all the standard libraries. So now we will use these standard libraries to create our half adder and full adder circuits. So after adding, so just verify the library setup. So ensure that the standard libraries and your custom library like this half adder and full adder design are visible. So now we are ready to start building the circuits. So first we will start the designing of the half adder circuits. So for that, just go to this cell option here. So now select the new view and here we need to give a cell name. So here I am giving the name. So half adder. And here we need to choose the view type like schematic or symbol. So presently we are creating the schematic of half adder. So for that, I'm just selecting the schematic. So after selecting the view type, so just click on OK. So here you will get the new cell. So you can use a plus and minus symbols on your keyboard to zoom in and to zoom out your cell view. Okay. So this is the workspace. So where we need to design the half adder circuit. So if you just observe the circuit of half adder. So the circuit contains one XOR gate and one AND gate, right? So now we need to access these XOR and AND gates from the standard libraries. So just go to generic 250nm logic gates. So here we will find the different logic gates over here. So among these logic gates, so I need an XOR gate. So here I need one XOR gate. So just drag that component onto your workspace. Just place it and click on escape. Okay. So now I placed one XOR gate and now we need to place one AND gate. So here we don't have an AND gate directly. So for that I am just taking an AND gate here. So as we know that inversion of NAND gate, we will get the AND operation, right? So here if we take the output from here, so we will get the NAND output, and if we connect the output to here, so with this outbar point, so we will get the AND operation. Okay. So after placing the basic gates, so now we need to connect the input and outputs, right? So for the half adder circuit, as we know that we have two input signals. So namely A and B, right? So here I am selecting an input port. So to rotate this or to rotate any component, you can just use or alphabet on your keyboard. So if you click or, so that component will be rotated. That component will be rotated, okay? So this is, so I am naming this input port as A. So if you want, you can change the font size also. Okay, so after giving the name and font size, so just click on OK. So now we need to select the second input. So for the second input, I am giving the name B. So okay. So now we need to connect these inputs to the XOR and AND gates. So if you observe, so both A and B are fed to XOR gate as well as AND gate. So by the end of the XOR gate, we will get the sum. So by the AND gate, we will get the carry. So here I am just selecting the wire. So this wire is used to connect the two components, right? So first I am connecting the inputs to the XOR gate. So after that I will connect inputs to the AND gate to get the carry output. So now we have connected the input ports to the circuit. So now we need to define the outputs. So here select the output port and connect it to XOR gate as well as. So the output from the XOR gate, we get the sum, right? So I am defined the name like sum. So again take another output and connect it to AND gate inverted output. Okay. So here I will get the carry. So just click on OK. So with this, so here we connected inputs A and B to XOR gate and we labeled the output as sum as well as, and we labeled the output from the AND gate as carry. So generally this is an AND gate and here we are taking the inverted output of the NAND gate. That is, here we will get the AND output, right? So after designing the circuit, so just to save your design. So for that, so just click on the save design option here. So just to verify that your half adder is connected correctly or not. Okay. So now we have created a half adder as a sub module. So now we will use this module in our hierarchical design to create the full adder circuit. Okay. So if you want, you can create a symbol for your half adder circuit. So for that you need so to create a symbol for your half adder circuit. So just to go to the cell option here and select the generate symbols option here. So here if you want, so you can change the options, like if you want you can change the symbol size also here. So after defining your specifications, so just click on replace. Okay, so with this, so this is the symbol for our half adder circuit. So we consider this half adder as a submodule to create the full adder circuit, right? So now we will use this module in our hierarchical design to create a full adder. So to design a full adder, so again go to the cell, take a new view and name this cell as full adder. So here the view type is schematic and click on OK. So this is the workspace. So where we need to design the full adder circuit. So as we know that, so by combining two half adder circuits, we will get the full adder circuit, right? And for these full adder circuits, we are having the three inputs, namely A, B and C in. And at the output side, we are having the two outputs, sum and carry out. Okay. So from the instance menu here, we need to choose the half adder cell. So we have created earlier and just drag this one and place it over in this workspace. So here we need two half adders, right? So after placing the two half adders, just click on escape. So now along with the two half adder circuits, so here we need one OR gate, right? So just place that OR gate also. So that OR gate will be present in this generic 250 nm logic gates. So here we don't have OR gate directly. So that's why I'm just selecting the NOR 2C. So this NOR 2C gate have the both outputs for the NOR gate as well as the OR gate. Okay. So after placing the all symbols and components, so now we need to give the input ports as well as the output ports. So for this full adder, we have three inputs. So first one is A, second one is B, and the third one is C in. So these are the three inputs we need to give for the full adder, right? So now I will connect these inputs to the circuits. So just select the wire. Next. To B. So after connecting the A and B inputs to the first half adder, so next we need to connect the inputs to the second half adder. So if you observe in the symbol of half adder, so here A and B are the two inputs. Here we have ground, here we have VDD, and here the first output is carry and the second output is sum. Okay, here. So if you see this full adder circuit, so here the sum output from the first half adder, so will act as a first input to the second half adder. Okay, and the second input for the second half adder, that is C in. So take a Y here and connect the sum output from the first half adder as a first input to the second half adder, and then connect the C in as the second input for the second half adder. Okay, now the sum output from the second half adder is our final sum, and the carry output from the second half adder, so we need to give to an OR gate to final carry output. Okay, so here the sum output from the second half adder, so we need to connect it to final sum. So this is our final sum. So after that we need to connect the two carry in the after that we need to connect two carry outputs from the two half adders to an OR gate. So to get the final carry output. So this is the carry from the first half adder and this is the carry from the second half adder. So after connecting the two carries to the OR gate, so here from the inverted output of the NOR gate, we will get the final carry out. So this is C out. Okay. So now we need to connect the VDD and ground for these both full adders. So now we need to connect the both VDD and ground to these half adders. Okay. So just take a wire. So I am just connecting the two grounds from the two half adders. And connecting the two VDDs from the two half adders. So after that, I will just connect a VDD over here. And I am connecting a ground to this ground wire. So now with this, the full adder circuit is completed. So now we need to give the voltage sources to the circuit. Okay. So first I will give the voltage source for this VDD. So we can apply either 5 volts or 3.3 volts. So for that, we need to go for this spice elements standard library. Here we need to select the voltage source. And here you will find different types of voltage sources over here. Among these voltage sources, I am selecting the DC voltage source for the VDD. So here at the bottom, we need to connect the ground to complete the circuit. Okay. So next. So here we need to give the input signals to this A, B and C in. So to provide the input pattern for these three inputs, so here I will select voltage source like. So here I will select the bitstream voltage source for the three inputs. So 1, 2, 3. Here I am taking the 3 bitstream voltage sources to give the input patterns for the 3 inputs. So now I am connecting the input signals to this bitstream voltage source. So like A, B and C in. And now, so now you can just copy the ground and you can paste it over here. So now we have provided the voltage sources and input bit patterns to our circuit. So if you want to change the input bit pattern, so just click on this voltage source. See here at the right corner, you will find the properties tab. So here you can modify the whatever pattern you want to give as an input. Okay. So after changing the pattern, just click on enter. So now after that, so if you want to view the output waveforms, so for that we need to include one command over here. So we need to include one command here. So for that we need to go for the spice command standard library. So here you will find an option like print voltage, right? So here under this you will find different types of print voltage options. Among these options you need to select the print voltage. So just select that one and drag it to the workspace and paste it to the nodes wherever you want to print the voltage of the variables. So here I want to print the values of 3 inputs and as well as the 2 outputs. So I just pasted the print voltage command, so wherever I want. So after placing the print voltage commands, so just save your design by clicking the save option here. So after that, so with this the circuit is completed. So now we need to run the simulation. So before going to run the simulation, so we need to set the simulation first. So for that we need to go for the setup simulation. So here, so we need to select the transient Fourier analysis over here, and here we need to mention the stop time, like I'm giving 100 nanoseconds, and here you need to give the maximum time step, so that is I'm giving like 10 nanoseconds. So after that we need to go for the general. So after that we need to go for the general option over here, and here we need to add the library files. So just to browse for the library files. So those library files will be present in the Tanner tools. So in the Tanner tools, we have an example folder. So in that we have one process folder over there. So then select the generic 250 nm and select generic 250 nm technology files. So in this folder, you will find the library file for this generic 250 nm technology. So just select that library file, click on open. So after opening the library file, so just move to the end. After that, give a space and enter TT. Capital TT you need to enter here. So after that, just click on OK. So now run the simulation. Now the simulation of the circuit is successfully done. So this is the waveform for this full adder circuit. So to expand this, just click on this option here. So this is the output waveforms we got for the full adder circuit. So you can analyze these waveforms with respect to the truth table of the full adder. Okay. So with this, the hierarchical design of the full adder by using the two half adder circuits is completed. So thank you everyone.